Okay, so today's lecture, we continue looking at forces, right? Because dynamics, it's that part of mechanics that deals with forces. We discussed about Newton's three laws, which were the first law, also called law of inertia. Second law is the law of acceleration, which also has the expression F equals ma. And the third law is the law of action reaction. We introduced in the previous lecture, we introduced the idea of weight, normal force, tension in the string. And today we introduce forces of friction. But before we introduce the forces of friction, I thought that it would be nice to see how exactly you work problems where the question is, please draw all the forces acting upon an object and please find out, usually the acceleration of the object, sometimes tension in the string if the object is connected by a string to other objects. So let me quickly go over example number one. Example number one says the following. It says that there is an object and the mass of the object is given. It's 5 kilograms. Excuse me. And the object is being pulled on a horizontal surface and the surface has no friction for the time being. And you are given this pulling force, which in magnitude, they say it's 20 newtons, and it makes an angle of 30 degrees with the horizontal axis. And that's all that is given. And the question of this particular problem is find out the acceleration of the object and find out the normal force, right? So the normal force. By the way, I am in the habit of changing the capital N so when I write the normal force, I write the capital N kind of straight and like this. And when I write the symbol for Newton, I usually make it curlier so that there is no confusion. This is the normal force. Those are the newtons, which is the unit for force, right? Okay, so first things first, you have to draw all the forces that act upon the object. The moment they give you the mass, you have to put the weight, right? The weight, which we know is the force that the earth acts upon the object, points directly down towards the center of the earth. The magnitude is the mass of the object times 9.8 meters per second squared. So that's one force. Another force, obviously, because it sits on a hard surface, another force is going to be the normal force. Let's recall the normal force is the force that the substrate, the surface, acts upon the object. And why? Because the object presses on the surface, and then the surface, the reaction is the surface acts upon the object with an equal in magnitude force and opposite in sense, and that's the normal force. And these are all the forces. And now, every time you're supposed to get an acceleration, you have to start from Newton's second law. Newton's second law says F equals ma, but in the case you have more forces, that F is the sum of these forces. So instead of F equals ma, its sum of all forces equals mass times the overall acceleration. Sum of all forces would be the pulling force, and F equals ma, it's a vector equation. Therefore, you're obligated to write the sign of vector above the force. So F pull plus the normal force plus the weight, everything equals mass times overall acceleration. And this is a vector equation, right? So vector equation. And we know, for instance, that every vector equation is equivalent to 2 or 3 scalar equations. Why do I say 2 or 3? If everything happens in 2 dimensions, like here, right? So everything, all the 3 forces act in the plane of the board, not one coming like that and in 3 dimensions. So if everything happens 2 dimensionally, then one vector equation is equivalent to 2 scalar ones. But if an object would be moving in space, being a 3 dimensional space, then one vector equation would be equivalent to 3 scalar ones. So where do the 2 scalar equations come from? From basically considering that every vector has the x component and the y component. You remember how we used to write vectors? So just remember and recall that we used to say that any vector A, for instance, in an xy coordinate system, it's equivalent to basically the following expression: a component of the vector times I hat plus a component of the vector times j hat. That is how all these vectors, so 1, 2, 3, and the acceleration, because all are vectors. So that's how all of these vectors are supposed to be written. Something I hat plus something j hat. And then when every force here is written as F pull along x I hat plus F pull along y times j hat plus n along x I hat plus n along y j hat plus mg along x I hat plus mg along y j hat equals mass acceleration along x I hat plus acceleration along y j hat. So when all this is written in unit vector notation, then all of the components which contain I hat can be separated, and all the components that contain j hat can be separated. And that's how we obtain the 2 scalar equations. So one scalar equation comes from considering the components of the vectors along x-axis. So that's one scalar equation. So basically, you have to think of component of the pulling force along x. So F pull along x plus n component of n along x plus component of mg along x equals mass times acceleration along x. So that would be one scalar equation. All of the vectors, but we consider only their components along x-axis. And another equation comes from, now we consider all the components of the vectors along y-axis, right? So now along y-axis. And along y-axis, then the situation is component of the pulling force along y plus normal force is component along y plus mg is component along y equals mass times acceleration along y. So again, one vector equation is equivalent to 2 scalar ones. One which is obtained by considering all the components of the vectors along x, and another one which is obtained from considering the components of the vectors along y. So, cleaning up, I don't even know where to squeeze stuff anymore. So cleaning up, it looks like this. We associate the x and y coordinate system. So this would be x, of course, this would be the y-axis. And what do we notice? The normal force is completely along y-axis. You don't need to decompose it because it's obvious how it is. mg, again, completely along y-axis. But F pull needs to be decomposed. So from the tip of the vector parallel to one of the axes, and this here is F pulled along X, and from the tip of the vector parallel to the other axis, and this here is F pulled along Y. I know that this component is F pulled cosine 30, and I know that the Y component is F pulled sine 30. So now let me replace stuff in this equation. So the components along X. So along X axis, what do I have? Component of F pull along X is going to be F pull cosine 30. So that's what I'm going to put here. So it's going to be F pull cosine 30. Then plus component of the normal force along x-axis, it's 0 because the normal force is actually 0 I hat plus n j hat. So basically it's nothing along x-axis. The component of the weight along x-axis, again it's 0, equals mass times acceleration along x. So that's what we have from this particular equation, which considers vectors along x-axis. Okay, let's now look along y-axis. So along y-axis, let's see. The component of the pulling force along y is F pull sine 30. So that's the first one. So F pull sine 30. Good. The component of the normal force along y, how would we write this? Yes, so for instance, just so that you recall, if I would draw a vector A, and I would tell you that the magnitude of A is 5, right? How would I write A in unit vector notation? 0 I hat plus 5 j hat. Therefore, the component of A along y-axis is A itself. And that's exactly the idea here. The component of the normal force along y-axis is the normal force itself. It's the magnitude of the normal force. Then, I'm here. The component of mg along y-axis, same thing. If I would draw here a vector b, for instance, right? And I would say that b is 3 units. How would I write b here? 0 I hat minus 3 j hat. So basically, what's the component of b along y-axis? It's negative 3. Who is negative 3? It's negative the magnitude of the b vector. Same goes here. mg is down. What's the component of mg along y? It's minus the value mg. So minus mg. And this equals mass times acceleration along y. So cleaning up, I have F pull, which is 20 newtons, right? So 20 cosine 30 equals the mass of the object, which is 5 kilograms, times its acceleration along x. And this other equation is F pull, which is 20 sine 30 plus the normal force, which we don't know how much it is, minus the mass times g, which is 9.8, equals mass times acceleration along y, right? So that's me replacing numbers wherever we have them. F pull is 20 newtons, sine 30, plus the normal force that I don't know, minus mg, the mass is 5, g is 9.8, equals mass times acceleration along y. And what do we notice? We have here two equations, three unknowns. Who are the unknowns? Acceleration along x, normal force, and acceleration along y. And if I look at two equations, 1, 2, 3 unknowns, you cannot solve, right? You need to have two equations, two unknowns in order to solve for them. So obviously something here you have to get rid of. And what are you getting rid of? You basically have to put in a little bit of common sense. What's the common sense? The common sense is the fact that you're pulling this crate or whatever it is, but the crate still moves along the horizontal surface. It's not flying up. Since it moves only along the horizontal surface, it has no acceleration along y-axis because it has no motion along y-axis. So basically, you have to impose that acceleration along y is 0, and then you reduce this to a system of two equations, two unknowns. So let me clean up stuff. Okay. So cleaning up, we come to the following two equations, two unknowns. 20 cosine 30 equals 5 times acceleration along x, and 20 sine 30 plus n minus 5 times 9.8 equals 0. What do we get from the first equation? We get acceleration along x, but that is what the problem was asking. The problem was asking for what's the acceleration of this object. And since we came to the conclusion that anyhow the object, since it moves along the x-axis, acceleration along x is all it has, then to answer the question, what's the acceleration? It's enough to say acceleration along x. So we get acceleration along x as 20 cosine 30 divided by 5, and that is, where is that answer here? 3.46, and the unit being meters per second squared. And from the second equation, we get the normal force because this was yet another question. And the normal force then equals 5 times 9.8 minus 20 sine 30. And when we solve that, we get 39. And these will be newtons, right? Because the normal force is a force, therefore measured in newtons. Bottom line, a lot of attention. Draw all the forces acting upon the object. Draw the XY coordinate system. Watch out to decompose the forces which are not completely along X or not completely along Y axis. You have to decompose them. And then you write sum of all forces equals MA. Take all the X components in one equation, and then take all the Y components in another equation. That's the procedure for all the problems. Okay? Another type of problem is the one that deals with the tension in the string. So let me quickly go over that. Example. So for the tension in the string, the example that is worked out is the following. You have an ideal pulley, therefore mass negligible. An ideal string, therefore mass negligible and cannot stretch. You have two masses hanging here. This is the M1, which is 2 kilograms, and this is the M2, which is a 3 kilogram mass. Right? Right. And here again, two questions. The acceleration of the system and the tension in the string. Start as always. Draw all the forces that act upon the object. Since they have mass, you quickly have to put their weights. M1G and M2G. Watch out, carry subscripts with you. Tension in the string, we discussed it yesterday. From the ends of the string towards the middle, same tension. So if there is one string, then it has the same tension everywhere. So TP, not T1, T2. Then you have to start with, again, sum of all forces equals MA. But because you have two masses here, not like the previous example, one horizontal surface, one mass, and then you had three forces and say F pull vector plus mg vector plus normal force vector equals mass times acceleration vector. No, here you have an m1 and an m2. Therefore, you have to write sum of all forces equals ma for m1, and then the sum of all forces equals ma for m2 separately. So first say I'm going to consider m1. First things first, you have to put in some common sense. You have to decide how these objects move. Obviously, in this case, since this is 3 kilograms and this is only 2, this will move up and this will move down. Why is it important to decide? Because it is customary to choose the direction of motion as the positive direction. So for this object, positive is taken up. So if I would associate an XY coordinate system for this, Y is pointing upwards. So let's see, sum of all forces for this one. T vector plus M1G vector. So T vector plus M1G vector equals M1 times its acceleration vector. That is writing Newton's second law for object M1. What did I say? From one vector equation, you end up with two scalar equations. In this case, when you're looking projection of all of these forces along X, you don't have any components. So the tension is completely along Y. M1G is completely along Y. Therefore, you have zero component from this, zero component from that, equals mass times acceleration along X is a zero then. And it's obvious, this object only moves up, down, never swings like this. So there is nothing along x-axis, but along y-axis, it's worth writing the components of these vectors. So let's see, along y-axis, component of the tension along y, since t and the positive y-axis are in the same direction, the component of t is along y-axis is t itself, right? Because you would write vector t as the magnitude of t times j hat of t. Then m1g. M1G is completely along y-axis, so its component is going to be M1G itself, but since it points in the negative y, it's minus M1G. So T minus M1G equals, and now let's see, M1 times acceleration of this object, which will be along y-axis. And since the object moves up, its acceleration is up, therefore, acceleration is expected to be a positive value. That's all for M1. And this is one equation, two unknowns. The two unknowns will be tension and acceleration. You move on to mass M2. Again, sum of all forces, and sum of all forces again are only two of them. Tension plus M2G equals, and now we pay attention to write M2 times acceleration. And again, you have to associate axes of coordinates. But here, since this moves down, the positive y is considered to be down, and of course, x again is perpendicular. It doesn't matter in this particular case. Therefore, when I take projections of t along y, now its component is going to be negative t because it points in the negative y direction. M2G, its component along y-axis is itself and with plus, equals M2 times, and now since the object moves down with an acceleration pointing down and the positive y is also down, then this acceleration is also has a positive component. And these two are the two equations, two unknowns that you need in order to solve for A and T. So let me copy them. T minus M1G equals M1A. And the second equation minus T plus M2G equals M2A. Two equations, two unknowns. The tension is one unknown. The acceleration is the other unknown. So let me stop by saying, see how when I wrote sum of all forces equals M1A, I did not say M1A1. And when I wrote sum of all forces equals M2A, I did not say M2A2. Why? Because the two objects are connected by a string which cannot stretch. Therefore, whatever acceleration this has up, the same acceleration the other one has down. It's not a different acceleration, an A1 and an A2. So when people ask here, what is the acceleration? They usually ask, what is the acceleration of the system? Because the system of two objects actually move as an entity. One part moves up, the other parts move down, but otherwise with the same acceleration. If you put here M1, A1, and here M2, A2, you end up with two equations, and instead of two unknowns, you would have three unknowns, and again, you could not solve. These systems usually are solved by adding the two equations. So what does adding equations mean? This side plus this side equals that side plus that side. So adding t minus m1g minus t plus m2g, the t and the negative t would cancel, and I would end up with minus m1g plus m2g. That is adding these, the left hand sides of the equal signs together. Then adding these two, I have M1A plus M2A. What we do, we give A as a common factor. So these two together means A multiplying the quantity M1 plus M2. And let me clean up. And this is how we first obtain the acceleration. So giving A as a common factor, A multiplies M1 plus M2, and then acceleration is minus M1g plus M2g divided by M1 plus M2. And replacing with the numbers, we get that acceleration apparently 1.96 meters per second squared. And once you know the acceleration, you go in either of the two equations, first or in the second one, and obtain the tension. So let me go back to the first equation. I'm going to keep tension on the left-hand side. So tension equals M1A plus M1G, and replacing M1 with whatever it is, 2 kilograms, acceleration 1.96, plus again 2 kilograms times 9.8. So doing this calculation, we end up with 23.5 Q. And these are again newtons, right? Because tension is a force. And you have some homework problems. Basically, repeat this, but for other combination of masses. Good. So these were the examples. And now let's introduce the next force, which is the force of friction. Okay. So the next force, which is the force of friction, basically, so forces of friction, we have them when the object is already sliding on a surface, and those are force of kinetic friction, or we have a force of friction even if the object is not yet moving. That would be called the force of static friction. So let's look at force of kinetic friction. So basically the idea is you have the crate and you are pushing it, so you know this F push, for instance, and the crate moves, right? So this is in motion. And then the question is, let's put all the forces acting upon the crate. So first of all, it's the pushing force. Yes. Then it's the weight, mg, of course. There is the normal force, of course, because it is on a solid surface. And since we said that there is friction, there is a force of kinetic friction, and I'm going to write it as F subscript K, force of kinetic friction, that basically is a force which acts upon the crate and of course opposes the motion. So if I say acts upon the crate, you have to make it literally with the point of application someplace on the crate, right? So acts upon the crate, opposes the motion, and it's very close to the interface between the crate and the substrate. It is obtained experimentally that the force of kinetic friction depends on the nature of surfaces in contact. Like for instance, if you have a block of wood on a wooden floor, there is a certain force of kinetic friction. If you would have a block of steel on a wooden floor, there would be another force of kinetic friction. If you would have a piece of ice on a wooden floor, it would be something else. If you would have a piece of steel on ice, it's another force of friction. So, forces of friction depend on the nature of the surfaces which are in contact, and also depend on how much the object presses on the hard surface. But the force that the object presses on the hard surface equals in magnitude the reaction, which is the surface acts upon the object and that reaction is the normal force. So basically, we know that the force of kinetic friction is proportional to the normal force. So again, it depends on how much the object presses on the hard surface. And as I've said before, if we go from proportionality to equality, we usually need, not usually, always, we have to multiply with a constant. That constant is the coefficient of kinetic friction, so that's the proportionality constant. This basically has in it that dependence of the force of kinetic friction on the nature of the two surfaces in contact. So this, we get it from tables. You have to say, oh, it's wooden block on wooden floor. There is one coefficient of kinetic friction. Who knows how much it is? Oh, it's a steel block on a wooden floor. It's another coefficient of kinetic friction. Oh, it's a piece of ice on a steel surface. It's another coefficient of kinetic friction. So this shows the dependence of the force of kinetic friction on the nature of surfaces in contact. Since force of kinetic friction is a force, therefore measured in newtons, and the normal force is a force, therefore measured in newtons. If you have newtons here and newtons there, it follows that the coefficient of kinetic friction is just a number, has no unit associated with it. So it's just a number, right? So that is the formula for the force of kinetic friction. Mu kinetic times m. And now if we consider force of static friction, so the idea is the following. Again, you have the crate on the floor and you are pushing this crate, right? So you do act with this force. So you're pushing the crate, but the crate is not moving, right? But not moving. And then the question is, oh, let's draw all the other forces acting upon this crate. And you have to say, oh, okay, it's the weight, of course, mg. It's the normal force, of course, because it sits on a hard surface. And if you stop here in the sense that you put only the pushing force, the normal force, and mg, if you only stop to this, if you consider sum of all forces equals ma, then the normal force in mg would make equilibrium because this object definitely does not hop up down. But also the pushing force has to be equilibrated by something, because if it is not equilibrated by anything, according to Newton's second law, F push would equal mass times acceleration along x, and the object would have an acceleration along x and would just go. So it's obvious you need to say, oh, there has to be a force of static friction. So it doesn't matter that the object is not moving. If you're pushing on it, there has to be a force that basically equilibrates that pushing force. Therefore, the force of static friction exists even when the object is not moving. When don't you have force of static friction? If you are not pushing the object. If you are not pushing the object, this doesn't exist, this doesn't exist. But if you push it, doesn't matter that the object is not moving, the force of static friction still exists. And basically the idea is, if you push with 50 newtons, since the object is not moving, force of static friction is exactly 50 newtons. If you push with 80 newtons and you're still not budging the object, the force of static friction has to be exactly that much, 80 newtons. So what's the conclusion here? The conclusion is that the force of static friction is variable, unlike the force of kinetic friction, which always has the same value, mu kinetic times n. The force of static friction is variable and varies between 0 when I'm not pushing at all, the force of static friction is 0, and a maximum value. What is that maximum value? So you have the crate. If you push 50 newtons, it's not moving. If you push 80 newtons, it's not moving. But let's say you push with 100 newtons, oh, and it started moving. Therefore, this force of static friction, which always equilibrates your pushing force at a certain moment, cannot equilibrate it anymore. That's called the force of static friction maximum value, and that equals the pushing force that would move, would start the object in motion. And for this force of static friction maximum value, we have a formula. We don't have a formula for the whole range because basically the force of static friction always matches the pushing force. But for the maximum value of the force of static friction, there is a formula. And the formula looks very much like the force of kinetic friction. It's going to be coefficient of static friction times n. And again, coefficient of static friction, just like the coefficient of kinetic friction, just a number, right? It doesn't have a unit associated with it. You take it from tables. So again, if you have a wooden crate on a wooden floor, coefficient of static friction is something. If you have a wooden crate on a steel floor, coefficient of static friction is something else, right? So we look them up in tables. It is also true that for the same pair of surfaces in contact, so wooden crate on wooden floor, let's say coefficient of kinetic friction 0.7, whatever. For the same wooden crate on wooden floor, the coefficient of static friction is more than 0.7. Let's say it's 0.75. So it is true that the coefficient of static friction is always greater than the coefficient of kinetic friction. So it is always harder to just start the object moving than once it's moving to drag it on the same substrate. Okay? And you have here some worked examples. So example 3, and then there is a homework 3 and example 4. And there is no homework here, but I would study those examples. It's not so paramount that you see me working those examples on the board because they all boil down to the same idea. Sum of all forces equals MA. Projection of the vectors along X give you one equation. Projection of the vectors along Y gives you another equation. And then it's your math talent into play to solve for the unknowns. So that's basically lecture number 7. I am going to, of course, send the link to this one. I have to admit, I'm disappointed that for the first time nobody came to this real lecture. Tomorrow, Friday, I am not going to have a lecture at 10 a.m. because I have something else scheduled. Therefore, I'm going to come tonight here at school, record, and send the link for the Friday lecture to everyone. So again, Friday at 10 a.m. I won't be here, but you will have the link to the lecture. Otherwise, I hope to see you guys on Monday at 10. Okay, that's all. I'll stop the recording.